I may have to repeat myself, but so that I don't miss this topic. Did anybody notice in the syllabus my mistake? Thanksgiving break is not the week of our 17th and 19th meeting. It's the week after. So the 24th and the 26th are Thanksgiving break dates. So that means next week we'll still be meeting. But I don't have anything else planned. So what I was thinking was we could at least use, rather than have the homework and exam due, well, we can still have it due during the Thanksgiving break. That gives you an extra week of review and without Thanksgiving in the way. But nominally, let's keep the homework and exam date on the 24th as a target. And you can go to the 26th if you like, or you can do it earlier. The exam's already up. But that gives us today and at least Tuesday to do reviews. And what I can do is, and that's Tuesday the 17th. What I can do is show up on the 19th, just open up the class on the 19th, and let that be a free-for-all. Anybody who's having problems that they've run across and we didn't cover in the earlier reviews, we can cover them there. So I'll just be there as a resource on the 19th. And then if you need it, you can take the week of Thanksgiving to complete the exam and your homework. And then we'll follow up on December 1st, which is a Tuesday. And we'll do some review then for the final exam, and more than likely bleed over into that following Thursday on the 3rd of December for final exam review. Because after all, we're covering 9 chapters. So I suspect it'll take more than one day. And then the final exam I've scheduled for December 8th. That hasn't changed. Okay. Any questions about that modification in schedule? I checked the 103 syllabus, and that one's correct for Thanksgiving break. Don't ask me how this one got messed up. It's a mystery. Let's see, did anybody else show up? No, we're still missing a few, but we're gonna get started and look at chapter 9. You'll notice that the review document, at the top of the review document, has, at the end of that line is a V1. That's version 1. Initially, when I put the review document together, it was about that thick and was just obviously too much. So I went in and split it up into 2 versions. And I think the better version is 1, but version 2 is valuable, and it's in Blackboard for repeating certain types of problems if you need extra work. Okay. But we're going to focus on version 1 here. And I want to be sure, before we get too far, that I introduce something that I mentioned in the lectures, but we didn't put into practice, was the shorthand molecular orbital structure. We've drawn the energy diagram, and that can be written in a shorter version, just like we did the electronic configurations with the 1s's, 2s, 2p, 3s, 3p, that so forth. You can do the same thing with the molecular orbitals. And you may have already seen some of those types of problems in the review document, and we'll spend some time on that today. I think we should do that today if we get to that. If we have to leave some other things out for Tuesday, next Tuesday, to be sure and get to that shorthand notation. Okay, so let me share review document version 1. Let's see here. That's version 1. Yep. Okay. So I'm going to move this out of the way and put this aside for me. And maybe blow it up a little bit, I think would be valuable. Maybe a little more. There we go. So we have sufficient resolution for the video for no other reason. All right, so one topic that we covered in the beginning of the chapter was extensions, further development of the valence bond theory and the localized electron model. And one of those corrections to the theory was hybridization, hybrid orbitals that were required to solve a problem. Let's see. I thought I heard somebody else show up. I'm looking for Lacey. Gee. So let me go down. No. I guess not. Okay. So back to the topic. So number 1 uses what we learned about hybridization. Atoms that are sp2 hybridized form how many pi bonds? There's somebody beeped in. Or maybe that was a returning person. Yeah. Yeah, it must have been a returning person. Ah, there we go. I got you, Jeannie. Now we're only missing Lacey. Okay. So it's hard to stay on track. sp2 hybridization. What's required for sp2 hybridization? Well, you hybridize one s orbital, not the one s orbital, but a s orbital, and 2 p's. Right? So those are hybridized into the sp2. So what's left over? Well, you know that you can have 3 p's. So you've got one out here that's unused, which means what? That is the one p orbital that is available for pi bonding. These will be sigma bonds. And this one is available. It can overlap with either another p orbital from the other atom, or it can it wouldn't overlap with an s bond. It would be a p bond. I mean a p orbital. Excuse me. So you only have one available. So if the atoms are sp2 hybridized, that means they only have one possible pi bond available. which is why this the answer to this one is B, which is 1. So you only have 1 pi available. Okay, it's fairly simple. You just have to understand how hybridization works in order to answer that question. Okay. Let's see if 2 is worth hanging on to. Yeah, we can do 2. Okay, so we have this molecule with 4 carbon atoms. And yeah, these are labeled 1, 2, and 3. Those are purely labels. They're not part of the molecule, the structure of the molecule. And then we have hydrogen here. We have another one there, another one there. And we have an oxygen double bonded. And then we have 3 hydrogens here. Okay. So the question here is, which one of these statements is false? So that assumes that all of them are true except for one, because we don't have any selections there that say 2 of the above or none of the above or those types of combinations. So all we have to do is find the one that's false. So if we take them in order, there are 10 sigma and 2 pi bonds. So let's see if that's true. 10 sigmas and 2 pi's. Okay? How many sigmas do we have? Sigma is a single bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's true. 2 pi's. Pi's will be associated with double and triple bonds. Here you only have 1 pi bond for double and 1 pi bond for double. So that was true. So A is true. How about B? C2 is sp2 hybridized with bond angles of 120 degrees. Okay, so C2 is sp2 hybridized and 120 degree bond angle. See if that's true. All right, what do we need for sp2 hybridization? We need, the VSEPR model says you need 3 electron groups to be sp2 hybridized. 1, 2, 3. So we're looking at carbon 2, 1, 2, 3. That's true. sp2 hybridized. And the bond angle for sp2 hybridization, because there are 3 opposing electron groups, they get as far from each other as possible. And that means that you have trigonal planar, which makes the bond angle 120 degrees. Why do we know that? Because if that bond angle is 120, this one is 120, that one is 120, add them up, you get 360. So this one's true. How about C? Oxygen is sp3 hybridized. Okay, we've only got 1 oxygen. Right? So what do we need for sp3 hybridization? sp3 hybridization means that you have a tetrahedral structure because you have 4 atomic orbitals that are hybridized to make 4 equivalent sp3 hybrids. Think of methane or carbon tetrachloride hybridization on the carbon, and that's your tetrahedral. Well, how many electron groups do we have around oxygen? You have to look at oxygen in terms of its Lewis dot structure. So how many electrons does oxygen have before it bonds? It has six valence electrons. How many have we used up? 1, 2, right? Because based on the formal charge, only one of those belongs to oxygen, and the other one for the other bond belongs to the oxygen, so it only has 2. That means you have 4 unaccounted for. Those are lone pairs. Now you can say something about the hybridization. 1, 2, 3 groups means trigonal planar sp2 hybridization. This one is false. That's your false one. If we went to D and said contains 28 valence electrons, it should, because we found the false one. But how do we know the valence electrons? Well, those are based upon how many belong to the atoms. So all your hydrogens only have 1, right? 1, 2, 3, 4, 5, 6. Carbon has 4. 1, 2, 3, 4, 16. And oxygen has 6. So that's 12 and 16 is 28. Okay, so that was true. We just verified it. E says there are some HCH bond angles of about 109 degrees in the molecule. So the clue there is the bond angle. What structure gives you 109-degree bond angles? Tetrahedral, which means you need sp3 hybridization, and you need 4. You need 4 electron groups. Okay, so which one has 4 electron groups? This one's only got 3. That one's got 3. That one's got 3. That one has 4. That's your sp3 hybridization with 109.5-degree bond angle, a tetrahedron. Okay, so that was number 2. All right, let's see if there's anything to be gained from 3. If we consider the following Lewis structure, what's the hybridization of atoms on oxygen, on first carbon, second carbon, and fourth carbon? All right, I won't even have to draw this one. So what's the hybridization on oxygen? Well, that oxygen has 2 bonds, which means 1 electron from one, 1 electron from the other one of its valence electrons, which means it has 4 left over, which means it has 2 lone pairs and 2 bonding pairs around it, which means 4. So the hybridization would be sp3. Right? So test-taking technique. Find out which ones have sp3, A and E. Forget about the rest of them. We'll focus on A and E. We might be able to differentiate between A and E with the second choice. Carbon 1, carbon 1. Carbon 1, what's its hybridization? It has 4 groups, which means sp3, just like the oxygen. That means that A is the answer. We could go through, right? But test-taking technique in multiple choice says, once you get the answer, move on. You can use that time better on other problems. Okay, how about 4? Okay, we can do this one. I won't have to draw this one either. We're interested in the hybridization of the carbon atom. Oh, no. That's no big deal. Carbon's got 4 bonds, sp3 hybridization. That's simple. C. Let's see. We've done one with oxygen that's double bonded. We know what that one is. It's sp2 hybridization. How about the central atom in AlBr3? Aha. Let's do this one. AlBr3. So what's the hybridization of the central atom, aluminum? So we need a Lewis dot structure. We need aluminum has 3 valence electrons. Bromine has 7 each. So that's 21 plus 3 is 24. Right? So we have aluminum in the middle. We have 3 bromines. Right? So that's 2, 4, 6. 18 electrons. Okay. So bromine needs 7 more electrons. 2, 4, no, 6, excuse me, 6. 2, 4, 6 times 3 is 18, right? Let's see if that's right. 2, 4, 6, 8. 3 times 8 is 24. Okay. So we've used them all up. So there's the Lewis dot structure. What's the hybridization on aluminum? Well, aluminum has 3 groups, which means trigonal planar, which means S and 2 P's. That's sp2 hybridization. Okay? Oops. Aluminum. Let's see, hybridization of bromine in BrF3. Let's do, yeah, this is worth doing. Okay, so 7 valence electrons because all halogens have 7. So there's 3 plus 1 is 4. 4 times 7 is 28, right? Okay, bromine's in the middle. Fluorine, fluorine, fluorine. Okay, we can put 6 of them around there. So that's 3 times 6 is 18. And electrons. Oh, we got to subtract 2, 4, 6 minus 6 is 4 electrons. Okay. Forgot to do the bonds. Okay. Now we have 4 electrons left over. Where do they go? Can't go on the fluorine. They're full. So we put them here. 2, 4. Now what kind of hybridization do you have with 1, 2, 3, 4, 5? 5 groups. VSEPR says 5 groups is trigonal bipyramid. Right? So you have 5 positions there. 3 of them are occupied by fluorines, and 2 of them are occupied by 2 lone pairs. Well, what kind of hybridization do you need to generate 5 lone pairs? You need 5 atomic orbitals. Right? sp3 is only 4. So you're going to have to draw on a d orbital, dsp3. And that's okay, because bromine is in the 4th period. It has ready access to d orbitals. Okay, so the answer is D. All right. Number 8, tetracyanoethylene has the skeleton shown below. How many of the atoms are sp2 hybridized? Okay, this one could get a little tricky because this is an organic molecule and you don't know organic nomenclature. So we've got to work from Lewis dot structures only. So let's see if we can do that. You're given the rough structure, the one where you start off with single bonds. That's nice of the authors. So we have 2, 4, 6 carbons and 4 nitrogens. And nitrogens. Now, what we have to assume in this case is that that's it. There are no other atoms. All right, no hydrogens, no missing hydrogens, not in this case. Okay, so let's see. How many valence electrons do we start with? 1, 2, 3, 4, 5, 6 times 4 is 24 for the carbons. And nitrogens are 5 each. So 1, 2, 3, 4 is 20. Okay. So we have 44 electrons. Now we've used up in bonding 2, 4, 6, 8, 10, 12, 14, 16, 18. So 8 from 4 is 6, and 1 from 3 is 2. 26 electrons that we have to do something with. So you start from the outside and work your way in. So we can have like that. We could have 6 there. We could have 6 there, 6 there, and 6 there. Okay, so that's 2, 4, 6. 4 times 6 is 24. So we have 2 electrons left over. So where do you put them? Well, the temptation is to put them on one of these carbons here. If we put them there, that's going to make it very difficult to make an octet for either of these. It's easy to make an octet here. If you've got 2 electrons there, you can take 2 here, make a triple bond. But that leaves these out. Right? Then these are going to be deficient. So the best place for that lone pair is in the center. Okay, that's the first trick. Then we need to make octets for both the nitrogen and the carbon. So this carbon has 2 bonds already. It needs 2 more. So rather than steal that one, let's steal from here. So let's take this one and this one and do that. And do the same thing for the rest of them. Okay. Now we've got octets for all of our nitrogens, octets for all of these outlying carbons. Now we need an octet for these 2 carbons. They already have 6 each. Well, this one has 8, but that one only has 6. So now we can take this lone pair and make a double bond there. Now, everybody's got an octet. And it's balanced, it's symmetrical, which is nice. Scientists like symmetry when they can get it. So now we can answer the question, how many of the atoms are sp2 hybridized, which means trigonal planar, right? 3 electron groups, right? This one only has 2, 1 there and 1 there. So none of the nitrogens are sp2 hybridized. How about this carbon? 1 group there, 1 group there. That's sp hybridized. sp hybridized, sp hybridized. So the only ones left are these 2 carbons. 1, 2, 3. 1, 2, 3. So you have 2 sp2 hybridized atoms. Both of them are carbons. That's why the answer is A. Now, I know that explanation probably blew by you pretty fast, which is a good thing that it's recorded. Then you can go back and look at it. Okay, let's see. Skip that one. Skip that one. Okay. How about 11? All right, we have these 3 molecules. And the question is, which molecules have at least one carbon atom is sp hybridized? Okay, so let's look at it. We got this one. Recognize that one as benzene. This one. And it's got 2 double bonds. I won't try to name that one right now. We're going to focus on the hybridization. And then this one. Okay. Now, which molecules have at least one carbon atom that's sp hybridized? What do you need to be sp hybridized? Oh, by the way, I think I mentioned it during the lecture. When we draw these organic molecules, anywhere 2 lines meet is a carbon atom, right? And that's why the formulas are down there also. And the formulas also tell you that for this one, there are 6 hydrogens, right? There's 1 there, 1 there, 1 there, there. Okay. For the next one, there are 8 hydrogens. So that means there's 1 here, 1 here, 1 here, 2 there, and 2 there. 2, 4, 6. I'm missing 1. H8. Oh, there we go. Okay. So what you're trying to do is make 4 bonds to carbons. That's just the way carbon works. And this one has 10. So there's 1 there, 1 there, 2, 4, 6, 8, and 10. Okay, now we can look at the electron groups around the carbons. Are there any that have only 2 groups? No, they all have 3 at least, some of them 4. So that means none of them are sp hybridized. Okay, what would you need to have an sp hybridized carbon atom? Actually, you can't get one in a cyclic compound. There's no way to put a triple bond in there. So you have to have a linear molecule, and you have to have 3 bonds to a carbon with something on this side. Could be a hydrogen, could be a lone pair. But you have to have 2 groups to be sp hybridized. So you can put another carbon over here, just as an example. And then what do you have? Acetylene, right? So every shade tree auto mechanic has a torch that runs acetylene and oxygen so they can cut through stuff. It used to be every coal miner had acetylene on their head. Only it wasn't in a tank. It was in a compound called calcium carbide, excuse me. Calcium carbide, you just add water to it, and the gas it generates is acetylene. And then you light it in your headlamp, and you go dig for coal. And just hope there's no buildup of dust. Because an open flame like that, I'm sure that's where most of the mine explosions came from before the advent of electric lamps. Okay. Let's see. Uh, 12, let's see, I'm time's okay. Which of the following statements is true? 12. Let's see, minimize that, okay. Electrons, is this statement true? Electrons are never found in antibonding orbitals. That's what that O means. It means orbital. Antibonding orbitals. Is that true? No. We saw during the last lecture that some electrons have to go into antibonding orbitals. So A is false. How about B? All antibonding molecular orbitals are higher in energy than the atomic orbitals of which they are composed. That's true. When you combine two atomic orbitals to make two molecular orbitals, one is lower in energy, one is higher in energy. The lower one is the bonding orbital, the higher one is the antibonding orbital. So B is true. How about C? Anti-bonding molecular orbitals have electron density mainly outside the space between the two nuclei. That's also true. It's characteristic of bonding molecular orbitals to have the electron density in some space between the two atoms that are bonded. Sometimes if it's a sigma bond, it's on axis. Most of the electron density is between the two atoms. If it's a pi orbital, it's between the two atoms, but it's off axis. So C is true. So D says none of the above are true. That can't be right. E says two of them are true. So that's why, oops, D is false. E is true. Okay. All right, let's see. That's kind of a trick question, I think, number 13. If 4 orbitals on one atom overlap 4 orbitals on second atom, how many molecular orbitals will form? That's just basic to the one of the premises, assumptions of molecular orbital theory. You have to have the same number of molecular orbitals coming out as you have atomic orbitals going in. So you would have 8. 4 plus 4 is 8 molecular orbitals in the molecule that forms. Oh, okay. 14. This is a question about magnetism. So let's get our definitions right again. Paramagnetism. Okay. Versus diamagnetism. So what's the difference? Well, they both imply magnetic field of some kind. And they refer to an element or a compound's response to a strong magnetic field. If there is a response and you can measure that force, they are paramagnetic. Those molecules respond. Diamagnetic means no response. Now, why is that? This only happens if you have at least one unpaired electron. Unpaired electron. Could be more than one. And this one is all paired electrons. Okay? So now let's look at the question. If a molecule demonstrates paramagnetism, responds to a magnetic field, which of these are true? The substance can have both paired and unpaired electrons. Is that true? Yeah. It can have all of its electrons paired except for one. That's all it takes. So Roman numeral 1 is true. How about 2? The bond order is not a whole number. A bond order can be a whole number, right? We saw examples of that. All you need for bond order to be a whole number is for the numerator to be an even number, right? If bond order is bonding minus anti-bonding divided by 2, then all you need is for this these two terms, when they subtract, give you an even number. Then divide 2 in an even number, you always get a whole number, right? It could be an even or an odd, but it would be a whole number. So the bond order for paramagnetism can be anything. All that's required is that unpaired electron. So we don't, 2 is not true. 2 is false. 3, it can be determined by drawing a Lewis structure. That is patently false. The problem with the Lewis structure and the theory in which it fits is that it cannot explain paramagnetism and diamagnetism. The localized electron model, which is part of the valence bond theory, says nothing about why paramagnetism and diamagnetism exist. Only the molecular orbital model answers that question. So 3 is also false. And 4, it must be an ion. No. An ion, obviously, would be unbalanced in charge, which means it could have 1 or more electrons in excess of positive charges. But it doesn't say whether they're paired or not. So 4 is also false. The only one that's true is 1. So that's why D is the answer. Okay. Let me see here. See if I tend to shift the board over time, so I need to pull it back. There we go. Get everything on screen. All right, so we got a half hour left. I know I'm going to run out of time, but that's okay because we got Tuesday and beyond, actually. Okay, so we're still on the subject of magnetism. The fact that O2 is paramagnetic can be explained by what? Remember the molecular electron structure for oxygen. This would be a good time to use shorthand notation. So if you look at the in this document, in the back, right, I've got the electronic structures right here, right? So you don't have to memorize them. So notice that oxygen is in this right-hand group, these two, oxygen and fluorine, dioxygen, difluorine. Those are the non-sp mixing elements. The ones on the left are the sp mixing elements. So that means for the non-sp mixing and your molecular orbitals derived from the p orbitals will have the sigmas bonding and anti-bonding on the extremes, and the pi bonding and anti-bonding in the middle. which, and another way to write that is, so O2, if we write the complete molecular electron structure, we would have a sigma derived from a 1s orbital and a sigma star derived from a 1s, right? Because you got two 1s orbitals, so you have to have a bonding and an anti-bonding, 2 in, 2 out. Then those are not shown in this chart. Those are down here somewhere. I'm just putting everything in. So you see that this is the complete molecular electronic structure. All right, so next is sigma orbitals derived from the 2s, bonding, anti-bonding. Okay. Now we come to the p's, the sigmas and the pi's derived from p's. Notice that you don't have any pi's derived from s orbitals, only from the p's. So the next one is going to be the sigma derived from a 2p, and then out here you have your sigma star derived from the 2p. And in the middle we have a pi derived from a 2p. Actually we have two of them. And then a pi star derived from a 2p. Okay? Now, we have to put electrons into them. So how many valence electrons for oxygen? 6 each. So that's 12 electrons. Each sigma can hold 2. And we're not going to go out here yet because you got to, Hund's rule says you got to fill them in energy order. So that's 2, 4, 6, 8, 10. We need 2 more. Did I do that right? 2, let's see, 6 and 6. Oh, no, I'm filling them up, not just valence. Valence is from here over. This is core. Right, so there's 4 electrons in the core. 2 from the 1s of one oxygen and 2 from the 1s of the other oxygen. So that means we have 14 actually. So over here, we have valence electrons because they're all the same energy level, 2, 2, 2, 2. Same prime quantum number. So that means we had, what, 6 and 6 is 12. 2, 4, 6, 8, 10, 2, 4, 6, 7, 8, 9, 10, 11, 12. Okay, so these will have 4, and these will have 2. And there are none there. Now, how do we make use of this format if we don't have these guys? We know that the pi's can have 4, right? Because in a triple bond, you have 1 sigma and 2 pi's. Possible, maximum. So you have 2 here, but you have 4 and 4 here for the pi's. So you can have another bond here, another bond here. And you only have 1 bond here. So what I'm trying to get at is, how can we look at that if we don't have those drawn below? And you can do that just to prove to yourself that this is the way the electrons go in. But you can have a maximum of 4 here. And you can have a maximum of 4 there. So if you say it's pi bonding with 4 electrons, means that all the spaces are used up. They're all paired, right? There's no potential for an unpaired electron here. But if you have a pi here, whether it's a pi or a pi star, it doesn't matter. If you only have two, that means both are unpaired because you have to put one in spin here and one in spin up there. You could have three there, and you could put two here and one there, which will still be one unpaired, and it's paramagnetic. But the idea is that for all the sigmas, you have 2, 2, 2, 2, and the pi's, you have 4. Okay? So that's how you write the shorthand. And I'm pretty sure that it's not important that you write the core unless it's asked for. All right. So let's see. Oh, I flipped that page already. Let me go back. No, I don't need that. I got it here. Oh, all right. So let's answer the question. 15. The fact that O2 is paramagnetic can be explained by what? A, the Lewis structure of O2. I just mentioned that the Lewis dot structure tells us nothing about electron pairing. Unless by accident. So Lewis doesn't explain it. Resonance doesn't explain it. The Lewis dot structure and resonance are both artifacts of the localized electron model. And that model says nothing about paramagnetism, dimagnetism. It can't explain them. So you write those off immediately. A violation of the octet rule, that doesn't say anything either, because that's also part of the VSEPR setup with the Lewis structures. How about D? The molecular orbital diagram of O2. Bingo. Molecular orbital model tells you all you need to know to deduce magnetism, paramagnetic or diamagnetic. And E, hybridization of atomic orbitals. That's still localized electron model, right? And it can't say anything. The only one that fits is the one that refers to molecular orbitals. That's D. Okay. Let's see, 16 gives you a shorthand. And in this case, we put parentheses around them, which is probably a smart idea, so that you can keep the numbers of electrons separate from all the other numbers that are inside the molecular orbitals. A species has the following molecular orbital configuration. This substance is what? Paramagnetic or diamagnetic? Well, let's see. First, if it's diamagnetic, then we're done. If it's paramagnetic, then we have to discern between A, B, C, and D. So, is it diamagnetic? We have to say that all are paired. Well, let's see. The sigma, 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 sigma. Those are all paired. How about the pi? Pi only has 2 electrons in it, and it can have a maximum of 4, and those 2 must be unpaired. So it's not diamagnetic, it's paramagnetic. And it's because we have 2 unpaired electrons, which is B. I'm going to skip 17 right now. We've done hybridization out the wazoo. Maybe we ought to do one hybridization. How about xenon pentafluoride cation? Let's see, 19. Xenon pentafluoride cation. Okay, xenon has 8. Fluorine has 7 each, which is 35, and 8 is what? 35 and 8 is 43, right? Minus 1, 42. So we have xenon in the middle. We have 1, 2, 3, 4, 5 fluorines. You have 6 around each one. Let's subtract these. 2, 4, 6, 8, 10. 32. Okay. Okay, now we have 246 times 5 is 30, right? And that's 2. So those two lone pair, that one lone pair, excuse me, has to go on the xenon. Now, what type of geometry does that represent? 1, 2, 3, 4, 5, 6. That's an octahedron. An octahedron means we need 6 bonds, or 6 bonds or groups. Right? So 6 groups means we need 6 hybridized orbitals. We can get sp3 gives us 4. We need 2 more. After stealing from D. And believe me, xenon has plenty of Ds. Okay, so that means 19 would be E. Okay, we're about 15 minutes away from closing time. And that just, I wanted to drive home the point there. When you're counting up valence electrons to do the Lewis dot structure, if the molecule is ionized, be sure to take that into account. For I3, it's got an extra electron, so you have to add that one to the valence. For xenon pentafluoride cation, we were short 1 electron, so you had to subtract from the total. Okay, let's see. We already did that one before. How many non-bonded electron pairs are in the molecule? Well, if you remember our drawing of the tetracyanoethylene, the only lone pairs on that whole molecule were assigned to nitrogens. And by the time we got through bonding, each nitrogen had 1 lone pair. Right? So you have 4 lone pairs in that molecule. How many electron pairs? 4. Let's see. Oh, bond order of He2 plus. Is that even possible? He2 plus. The example we had in our last lecture was that He2 was impossible because the bond order is 0. But what about this one? Right? If we draw the energy diagram, and we have helium here, helium there, so 2 heliums, and we're only going to use the valence shells for helium, which actually is 1s. 1s. So we get a sigma star and a sigma. Okay? So how many electrons here? Right? Helium's got 2 protons, got to have 2 electrons. So we have 2 electrons here. So that's 4 electrons, except we're missing 1. So we really only have 3 electrons. So 3 electrons that have to be placed. So you have 1, 2, 3. Now we can do the bond order. So that's 2 here minus 1 divided by 2 equals 1/2. That molecule is possible. It's a weak bond. It's only got a bond order of 1/2. It's not even a complete, it's not even a single bond. But it is possible. That's why the answer for this one is B. Okay. keep sliding that one out of frame. Let's see. Do we need to dwell on 29? Ooh, that's a good one. Okay, for which of these diatomics would the bond order become greater if an electron is removed, converted to a single positive charge ion? So we have A, B, C, D, and E. So we have B2, carbon, phosphorus, fluorine, carbon, phosphorus, fluorine, and sodium. Phosphorus. Yeah, 2, 2, 2, 2. I don't think disodium is even possible. But we'll stick it up there anyway. Yeah, I want to save myself some time. All right. So boron is in the second period, carbon's in the second period, phosphorus is in the third, fluorine's in the second, and sodium is in the third. All right, so we're only going to draw the electronic structure for the valence shell. So with boron, we have, if we have a plus, how many valence electrons do we have? Right, boron is 3, and 3 is 6, so now we only have 5. Okay. To answer this question, for which would the bond order become greater, right? Strengthen the bond. So we got to look at both this one and that one. So we'll draw this one, and that'll lead us to the next one. All right, so boron has a 2s, 2p. So it's going to have a sigma and a sigma star from a 2s. Right? Is that going to be enough? No, because we have 6 electrons here and 5 here, so we need another orbital. Right? The next one in order for boron is pi, right? Because boron is sp mixing. So instead of sigma, sigma star, and pi, pi star in the middle, it's pi and sigma, and then pi star, sigma star. So this one is going to be a pi from a 2p. So we have 2 here, 2 here, and 2 here for that one. And then for this one, we take 1 away from here. So these are the same. This one is only 1. So what's the bond order for this one? It's 2 plus 2 is 4 minus 2 is 2. Divided by 2 equals 1. Let's do it this way. Bond order, 1. How about this one? It's 2 plus 1 is 3. Minus 2 is 1. Divided by 2 is a half. So the bond order went down in this case, and we're looking for the one that becomes greater. How about carbon? Carbon will have the same set here. Okay. Yeah, that's right. And each carbon has 4. Right, 4. So it'd be 8 total. 2, 4, 8. Okay, take one away. These are the same. This one is now 3. So 2 plus 4 is 6, minus 2 is 4, divided by 2 is 2. Bond order 2. Subtract from this one, and you get 2 plus 3 is 5, minus 2 is 3, 1.5. So what's the pattern emerging here? If you lose an electron from a bonding orbital, your bond order decreases. If we were to lose an electron from an anti-bonding orbital, we would expect the bond order to go up. So that's what I'm looking for. How about phosphorus is going to give us a decrease as well. I'm racing against the clock. So let's go to fluorine. Fluorine has a sigma 2s, a sigma star 2s. Now fluorine is not sp mixing. So it's going to have, the next one is sigma 2p, and then pi 2p, and then pi 2p star, and if we need it, sigma star. Okay, so each fluorine has 7 valence electrons, because we've only drawn the valence molecular orbitals here. So that's 7 plus 7 is 14. So for the neutral molecule, it's 2, 4, 6, 10, 14. Okay, so we don't need this one. It's all used up. So what's the bond order here? Well, let's see. 2, 4, 8, minus 6, divided by 2 equals 1. Right? Yep. Now, if we ionize it, which one comes off? The highest energy. So we lose one of these, which means now, instead of subtracting 6, we subtract 5. So difluorine, when it's ionized, becomes stronger bonded. And we could do sodium as well, but it turns out it decreases in, it's a decrease like the others. All these are decreases. Difluorine is the only one that increases with a loss of an electron. And simply because of where the loss occurs. The loss occurred in an anti-bonding orbital, which strengthened the bond. Whereas the rest of them, the loss occurred 1 electron from a bonding orbital, and that decreased the strength of the bond. Okay, I got 5 minutes. Let's see. This one, $30 is going to require Henry Ford. And what I mean by that is, set it up so that you can draw the molecular orbital structure the same way each time for every one, and then all you have to do is fill in the electrons. So I'm not going to spend time on this one. The gist of number 30 is you determine the bond order of each of these species: O2, O2 minus, O2 2 minus, O2 plus, O2 2 plus. Determine the bond order. And the one with the highest bond order will have the largest dissociation energy. That is, how much energy does it take to break that molecule apart? And as it turns out, the highest bond order is for O2 2 plus. Why? Because the loss of those 2 electrons to give it a 2+ charge came, both of them, from anti-bonding orbital. Now that cannot be explained by the valence bond theory or any of its models. Only the molecular orbital theory can explain that increase in dissociation energy. Okay. 31, you just have to go down, calculate the bond order. You need to draw the molecular structure, right? And you have to be mindful of the fact that using this information that's given to you here, right, you can tell that the order of those molecular orbitals is determined by whether or not they have sp mixing or not sp mixing. Sp mixing is anything on the left, nitrogen and left, oxygen or right. And let's see, are all of these in the same period? Carbon, no, phosphorus. You can extend, what group is phosphorus in? Phosphorus is below nitrogen. So phosphorus should also be sp mixing. Yeah, phosphorus should have sp mixing, which means even though its orbitals are derived from 3 s's and 3 p's, that they will also be in the same order as the 2 s's and 2 p's for anything with mixing on this side of the chart. Fluorine, okay, phosphorus is the only odd one in there. The rest of them are all second period. So you just have to understand that phosphorus follows the same pattern of mixing as nitrogen. And it turns out that to answer the question, once you draw those structures out, then you can determine the bond order and find that the bond order only for dicarbon gives you a bond order of 2. That's it. The rest of them are either 1s or 3s. Okay, I'm out of time. So let me mark. Got up to 31. And I'm going to mark that one. And on Tuesday, we'll pick it up there, which will be, let's see, today's the 12th of November. And then Tuesday will be 17th of November. And we'll do some more review because we haven't gotten into some things that really need to be hashed out. And what I'll do is in 15 minutes, I'll reappear on the CHEM103 Zoom link, and we can talk about any problems you're having with your labs, any questions you may have. Okay, let's stop the share. And let's see, did I miss anybody? Who was I missing? Lacey, that's the only one I was missing. Okay, I don't remember seeing Lacey. Okay. If I don't see you in a few minutes, have a good weekend. See you on Tuesday.
Hey, Dr. Bly, I had a question.
Certainly.
When is the exam going to be due?
Oh, that's right. You came in late, didn't you?
Yeah.
Okay. Let me go back and correct my mistake. In the syllabus, I've got the Thanksgiving holidays in the wrong place. For all my other syllabi, the Thanksgiving holidays are correctly placed. But for CHEM101, I moved the Thanksgiving holidays up a week. I'm saying in the syllabus as it's given, we've got classes on the 17th and 19th are in the Thanksgiving break, but they're not. So we will meet on the 17th. Thanksgiving break occurs for us the 24th and the 26th. So that being said, I'm just going to leave the homework and exam 7 due dates the same. Right?
Okay.
They'll be during the Thanksgiving exam, Thanksgiving break, but you can do them ahead of time if you want, whenever you feel comfortable, because the exam's up already. Or you can do them during the Thanksgiving break. And then that will move the review for the final exam to Tuesday, December 2nd, December 1st, excuse me. Tuesday, December 1st, we'll do an exam review. That Tuesday, we can do an exam review that Thursday too. I think it probably will need that because we'll be working on 9 chapters.
Right.
But the exam date hadn't changed. It's just that the Thanksgiving break did change.
Okay. I was just wondering. That was all.
Yeah, apologize for the mistake. I was really kind of concerned there for a while in the beginning because I usually make a whopper mistake every semester. I just missed catching this one until now.